Hi everyone, welcome to our walkthrough for CSM 16B, worksheet number 2. I'm Anthony. So for this section, first thing we're going to be covering is complex numbers. So a complex number is a number of the form z equals a plus bj, where j, unlike the real numbers that we have encountered in the past, has a different property. That is, j squared is actually a negative number. J squared equals -1. So the expression of z into a plus bj is what we call the rectangular form of complex numbers. We call a the real part of z, and we call b the imaginary part of z. So we note that the imaginary part is not imaginary, it is real. Okay. So in terms of the computations of complex numbers, we just treat j as a separate variable and do computations accordingly, with the property that j squared is equal to -1. Then we have Euler's formula, which is probably the most important property of complex numbers in 16b. Euler's formula states that e to the j theta is equal to cosine of theta plus j times sine of theta. Okay? Its derivation can be given using power series, which we will not elaborate in this walkthrough. Okay, so with this Euler's formula, we can actually write our rectangular form of complex numbers into another form, which we call the polar form. So to write things in polar form, we have to express it in terms of r times e to the j theta, where r is greater than or equal to 0. Okay. So to convert between the two forms, to convert from polar form, let's say given z equals r times e to the j theta, we want to convert it to rectangular form. We just express e to the j theta as cosine of theta plus j times sine of theta. Okay. So that is equal to r times cosine of theta plus j times r times sine of theta. Okay. And then we have a rectangular representation of things. To convert otherwise, we're essentially trying to find r and theta such that a plus bj is equal to r cosine of theta plus j times r sine of theta. Okay? So, since j is just a separate variable, we know that a is equal to r times cosine of theta and b is equal to r times sine of theta. Okay? We take the square of both sides and add them together to see that a squared plus b squared is equal to r squared, because cosine of theta squared plus sine of theta squared is equal to 1. Okay? And so r is equal, since we know that r is no less than 0, it's non-negative by default, by definition, we see that r is equal to the square root of a squared plus b squared. Okay? To find the value of theta, we simply divide the two equations to see that tangent of theta is equal to r times sine of theta over r times cosine of theta. Okay? And that is equal to b over a. And so theta is equal to arctangent b over a. Okay? This is just how we convert between the two forms. We observe that to express a complex number, we would actually need two real numbers. So essentially, we devised a scheme to actually represent this number in a two-plane, just as if we're in r squared. So if we're given a rectangular form, z equals a plus bj, we just find the coordinates ab, and note that this point is actually just our complex number, z equals a plus bj. On the other hand, if we are given the polar form, r times e to the j theta, we just first find the radius r, we then find the angle theta, and then we just find the complex number as desired. All right, so then we're just going to jump into the questions. If you want to take a few minutes to think about the question yourself, just pause the video. Okay, and then 3, 2, 1, unpause. All right, so for part A, we want you to convert between the polar and the rectangular forms. So the first part says that I want to convert 10 plus 12j into polar form. So as we said, r is equal to the square root of 10 squared plus 12 squared. Okay, so that is equal to the square root of 244, which is then equal to 2 times the square root of 61. Right? Okay. And then the angle of this complex number, which is just a theta, is just the arctangent of b over a. Okay? So b over a. Okay. And so we see that z is equal to 2 times the square root of 61 times e to the j times arctangent 6 over 5. Okay. All right. So for the second question, we want to convert 22 times e to the 23j to rectangular form. So we just simply expand this whole thing using Euler's formula. So we see that 22 times e to the 23j is equal to 22 times cosine of 23 plus j times sine of 23. Okay? And that is equal to 22 times cosine of 23 plus 22 times j plus j times 22 sine 23. Okay. And for part B, we want to plot the following on a polar grid. So the first part asks us to plot 2. Number 2 has real part 2 and imaginary part 0. So we just plot on the coordinate 2, 0. Okay? I mean, if we really want to think about it in terms of polar form, we know that its magnitude, which is the r, is just 2, and its phase, which is the theta, is just 0. Okay? So this is just 2. And with a similar logic, we know that 2j, in terms of the rectangular form, its coordinates would just be 0, 2. Okay? And so that would just be 2j. I mean, if you want to think about it using the polar form, same thing. The magnitude still 2, the norm still 2, but the phase, which is again the theta, it would be pi over 2, which is 90 degrees. All right, so for the third question, we're asked to plot 2 plus 2j on a polar grid. So in terms of the rectangular form, the coordinates would just be 2, 2, right? So this would just be 2, 2. All right, and that concludes our solution for part B. All right. Okay, off to part C. We want to calculate the magnitude and the phase of the following complex numbers. We should note that real numbers are all complex numbers. Okay. So the magnitude of a complex number is just what we explained let's say if I have a complex number, z equals a plus bj expressed in a rectangular form, then the magnitude of the complex number, or its norm, would just be the square root of a squared plus b squared. Okay, and the phase, which we'll express in this notation, or its angle, would just then be arctangent of b over a. Okay, so basically we're just going to plug in the formulas. So for this first part, we are trying to calculate the magnitude and the phase of the number 2. Okay, so we notice that let's say z equals 2, the norm of z is actually equal to 2 squared plus 0, which is then 2, and the angle or the phase of the complex number would just be arctangent of 0, because b is 0, doesn't have an imaginary part, the imaginary part is 0. Arctangent of 0 is still 0. And so that concludes our solution for part 1. Okay, so for part 2, first thing we're going to try to do is that we're going to try to write this whole thing in terms of rectangular form, right? So if z is equal to 2 over 2j, this is obviously not of the rectangular form. First, we try to cancel out the 2's on numerator and denominator, and then we multiply j on both the numerator and the denominator. So j over j squared, because j is not 0, obviously. And then that will be equal to j over negative 1, which is equal to negative j. Okay, so the real part is 0, imaginary part is negative 1. Okay, so the norm or the magnitude would then just be 1 squared plus 0, which is equal to 1. And the angle or the phase of this complex number is just arctangent of negative 1. Oh, we have an issue, right? Because we're trying to divide negative 1 by 0, right? In this scenario, it would just be better if we just try to draw out the complex number, and the coordinates, right? So this is the real part and this is the imaginary part. We notice that z corresponds to the complex number negative j. And so its phase would then just correspond to this angle. So this really doesn't make any sense. Okay, but instead we can simply use the coordinate system to find out that the angle of z, or the phase of z, is actually equal to 3 over 2 pi. Obviously, these are all in the unit of radians. Okay. And then for a third part, we know that z is equal to 3 over 5j. So this real part is 0, imaginary part is 3 over 5. And its norm, or its magnitude, would then just be 0 plus 3 over 5 squared, which is then equal to 3 over 5. And the angle, we have the same issue. You can see we have the same issue, because a in this case would then still again be 0, right? Which doesn't make any sense. In that scenario, we simply draw the coordinates. We realize that this is actually corresponding to this number. And so its phase would then just be 90 degrees, or 2 over or pi over 2. All right. So for this very fourth question, we're trying to find the magnitude in the phase of this quotient of complex numbers. This might be a little bit complicated, but it won't be that complicated if we know a property, which is the norm or the magnitude of a quotient. Here A and B are just complex numbers. It doesn't have to be real, could be complex numbers, is equal to the quotient of their norms. Okay? So this is really helpful. Okay? And so we do not need to turn this directly into rectangular form, but rather we directly see that the norm of z, let's say z is this number, the norm of z is actually the quotient of the norms. So it's a norm of 1 plus 2j over a norm of 9 plus 7j. Okay, so this would be 1 squared plus 2 squared over 9 squared plus 7 squared. Okay, which would then be square root of 5 over 130. And the angle of this complex number will then just be the angle of 1 plus 2j minus the angle of 9 plus 7j. Okay? Which is just the arctangent of 2 over 1 minus the arctangent of 7 over 9. The remaining calculations is left for the calculators. All right. Okay. So we notice that the angle of a quotient is equal to the angle of A minus the angle of B. Right. All right. So these properties, these can all be proved fairly easily if we're in polar form. Right. So if we have A being equal to R1 e to j theta 1 and B being equal to R2 times e to the j theta 2, then A over B would then just be R1 over R2, assuming that R2 is not 0, which it couldn't be since B is on a denominator, times e to the j theta 1 minus theta 2. And that pretty much says everything. Okay, so we see that the norm of the quotient is just R1 over R2, which is the quotient of norms, and the phase of the quotient, which is just theta 1 minus theta 2, is just the difference between the phases. All right, now we move on to part D, where we are asked to show that 1 over j is equal to negative j. This is something that is sort of intuitive, and it will be but it's not like immediate if you wasn't too familiar with complex numbers. So what we're gonna do is that we're gonna multiply both sides of the fraction by j. So we get 1 over j being equal to j over j squared. And j squared we know is equal to negative 1. So we have j, that being equal to j over negative 1, which is equal to negative j. Okay. And we have our statement. Okay. Now, a complex number has a complex conjugate, z conjugate, being equal to a minus bj. In polar coordinates, the equivalent expression is the conjugate of r times e to the j theta is equal to r times e to the negative j theta. So the reason why this statement is true is that if we think about it, r, actually going to write in a different color, r times e to the j theta is equal to r times cosine of theta plus j times sine of theta. Okay? Whereas r times e to the negative j theta, we can just move the negative sign a little bit back into its phase. That is equal to r times cosine of negative theta plus j times sine of negative theta. Okay? And since cosine of negative theta is equal to cosine of theta, and sine negative theta is equal to negative sine of theta, we see that this is equal to r cosine of theta minus j sine of theta. And so it is the conjugate of r times e to the j theta. Okay? So in polar coordinates, the equivalent expression is the conjugate of r. So the conjugate of r times e to j theta is equal to r times e to the negative j theta. All right. So we want to prove graphically that the sum of any complex number and its conjugate is always real. I mean, if we are really trying to prove it algebraically, just write out the rectangular form, which is equal to a plus bj. And its conjugate would then just be a minus bj, and their sum must be 2a, which is real. Which is real. Because the imaginary parts, they just cancel out. Okay. So if we're given an arbitrary number, let's say z equals 1 plus I, arbitrary enough. Not quite, but should work. We should draw it in the coordinates. So we have the real axis, the imaginary axis. Okay. And the number 1 plus I corresponds to the point in the coordinate 1, 1. Okay, so this is our number 1, 1. Okay, I should write it as 1 plus I. 1 plus I. Its conjugate is just 1 minus I, which corresponds to coordinate 1, negative 1. Right, so 1, negative 1. So that is 1 minus I. We note that these two vectors, or these 2 points, they're just symmetric across the real axis. Just symmetric across the real axis. And recall how we add together 2 vectors? We find a parallelogram. Okay, right here. And their sum would just be this. And the result would then be 2. Okay? Since these 2 are symmetric across the real axis, we add those together, they cancel out. And the resulting vector is just part of the real axis. All right, I mean, you'll get the same result no matter what kind of vector you're using, but that's basically the idea. All right, so off to part F. Recall that Euler's formula states that e to j theta is equal to cosine of theta plus j sine of theta. As I said, this is probably the most important property that we want you to know about complex numbers in 16B. So now using Euler's identity, we want you to show the following identities, which show that sinusoids are sums of complex exponentials. Okay, so the first thing that we're going to do, because the only thing that we can use is Euler's identity, so the first thing that we're going to do is that we can find multiple values of theta. It might be meaningful for us. So first equation that we're going to write is obviously just the Euler's formula itself, which states that e to j theta is equal to cosine of theta plus j times sine of theta. Okay? And then we write something else. We observe that there is this negative j theta in the exponential, in the exponent. So we can simply try and write e to the j negative theta. This is equal to cosine of negative theta plus j times sine of negative theta. And since cosine of negative theta is equal to cosine of theta and sine of negative theta is equal to negative sine of theta, we see that this is equal to cosine of theta minus j times sine of theta. All right, we then add the 2 equations. Together to see that 2 cosine of theta, because the sine terms, they just cancel out. On the left-hand side, we see that this is equal to e to j theta plus e to a negative j theta. Okay, so we see that cosine of theta is equal to 1/2 times e to j theta plus e to a negative j theta. Okay, Similarly, we can just subtract the two equations from each other. So similarly, subtraction gives e to the j theta minus e to the negative j theta being equal to 2j sine of theta. So in this case, we see that the cosine terms, they cancel out each other. So we see that sine of theta is equal to 1 over 2j times e to the j theta minus e to the negative j theta. And that concludes the proof for this question.